Hey guys, welcome back to another lesson. My title is getting cut off. Let me just move the camera up. There we go. Okay, today we're going to talk about the remainder and factor theorems. Okay, this is going to be going back to division a little bit and some usefulness when it comes to division. Now, some of these properties we talked about in the past a little bit. There's one property that is pretty darn cool, and we're going to talk about today. It's called the remainder theorem. Okay, the factor theorem. We discussed bits of it already, but the remainder theorem, that's the main goal for today, okay? So just to start out, let's say I have this polynomial, I'm dividing it by x minus 3. Now, instead of using long division, I use synthetic division just because of the effectiveness of how quick it is, okay? And clean. It's a little bit cleaner for right now. So when I do that, I have the coefficients for each part up here in the very top of the division problem. And then what I'm dividing by, I put the value opposite of it, right? Put 3 over here and solve. So this down here would be what? Negative 3x minus 4, and then your remainder, which is this negative 8. Okay, so that's your remainder. Okay? Now, what I'm going to do, in fact, let me just move here just a little bit closer so we can see this a little bit better. There we go. What I'm going to do is now take the same polynomial and I'm going to plug 3 in and evaluate it. Now, why am I going to do this? Well, you'll see. So when I plug this in, I get negative 3 times 9 plus 15 plus 4. Okay? Let's continue to simplify this. Negative 27 plus 15 plus 4. That gives me a negative 8. Okay? This is quite curious. If I take what I'm dividing by and substitute it into this function, I get the same answer as the remainder as if I divided it. That's an interesting little behavior, interesting pattern, interesting phenomenon, whatever you want to call it. But that's really cool. So let's think about this for a second. Would that work for every single problem? So for instance, if I plugged in f of 2 in this guy, is that going to be the same thing as me dividing by that polynomial by 2? And the remainder would be the same as this guy. And it would. It would work out. And this is going to work every single time. Okay? Now, why is that the case? Well, let's just talk about it real quick. If I were to multiply this x minus 3 times this polynomial, and by the way, of what's left, this would be what, x minus 3 at the bottom, how we write a remainder. So if I multiply this entire thing by x minus 3, I get the original, okay? Just, let's do a basic example. Let's say I did 3, okay, if I'm gonna put 3 into 14, goes into that, what, 4 times, so that's 12, we get 2. So this is my remainder, right? And I could rewrite this. That 14, okay, is equal to what I divide by, divisor, times 4 plus my remainder. So here's my remainder. Here's what I'm dividing by, right? Oops, sorry. There we go. Here's what I'm dividing by. Okay? I could do the same thing with a polynomial, right? This guy right here is equal to this times this. Okay, plus my remainder here. Let me go ahead and rewrite it. Let's see, negative 3x squared plus a 5x plus 4 is equal to x minus 3 times negative 3x minus 4, okay, and what, minus 8 over x minus 3, just like that, okay? So, why is the remainder the same thing as this guy, okay? So, let me just make this more generic for a second. Okay, so this is my function right here, f of x. Here's what I'm dividing by, and let's just make that, and I'm sorry for this, I keep moving the camera. Let's make this guy, I don't know, x minus a, and then this is some function that I have afterwards, plus my remainder over here. Okay, see how it's a direct correlation to each part? Okay, so let me go ahead and rewrite it on this whiteboard. Okay, so I just rewrote it up here. Okay, make it a little bit easier so that we can do this together. There we go. Okay, and I want to evaluate this function, right? So if I were to plug in the value that I'm dividing by, right? So this is what we are dividing by. Look what happens, okay? So if I plug a into this function, the first part becomes a minus a. The second part is our function q times a plus my remainder, okay? A minus a becomes 0 times q of a plus my remainder. Anytime I multiply by 0, it's going to cancel out whatever it's being multiplied to. So f of a just becomes my r value, which is the remainder. How cool is that? That something very simplistic is out there in the open for us to use. Now, let me go back to this guy over here. Okay, so we just put this down. So going back to this guy, just to kind of connect the dots here. My divisor was 3, right? I was dividing by 3. So if I plug 3 into here, I get what? 3 minus 3, which becomes 0. 0 times this guy here, okay? And I should put this outside the parentheses, I apologize, okay? Will give me 0, and then this negative 8 is what's left, my remainder, okay? A very interesting property, and one that we could take advantage of. It just depends on what the polynomial is. If the polynomial is really complex, well, maybe I want to use a little bit of synthetic division to evaluate it, then plug in the number in, okay? Let's go ahead and take a look at an example. Let's put this into practice, okay? This will make more sense when we do that. So here we go. Example 1. If I can find it here on my assignment list. Here it is. So example 1. So here's my first example, and I'm going to find what f of 4 is. Now, instead of plugging this back into here, I'm going to go ahead and use synthetic division and get the same answer. So here we go. Put the 4 on the outside. The coefficients I put here. So that's a 3, negative 2. Now, there's no x squared. I'm going to put 0 as a placeholder. 5, and then 2. Put plus signs here. And carry down the very first value. It might look like I'm going through that part quickly, but we did a lesson on it already. All right, so now we evaluate. So 4 times 3 is going to be 12. Add these up, I get 10. Multiply, I get 40. Add up, I get 40. Oh, this is going to be fun. Multiply, I get 160. Add, I get 165. And then for the last step, multiply, I get 660. Add, I get 662. Okay? This is my remainder, right? The last part of this is always the remainder. And that is my answer. F of 4, if I plug it into this function, would be 662. Right here. Okay? You could check. If you plug 4 in for each x value, simplify, you would get 662. Okay? That just blows my mind, right? We're using division to evaluate. Who would have thought? Huh. That's really cool. Ready to try another one? Okay, let's do one more together. Let's try this one. So this will be example 2. Okay, so here's my next function, and I want to figure out what f of 3 is. And I'm going to use synthetic division. So I'm going to go ahead and put 3 here. The coefficients go up top over there. That's going to be a 3, negative 6, 1, negative 11. We're going to add and then bring down the very first value there. Okay, now let's go ahead and multiply and see what we get. Multiply, we get 9. We add, we get 3 again. Multiply, we get 9 again. Add, I get 10. Wait, so far so good. And then for the last one, multiply, I get 30. Add, I get 19. The last result is the remainder, and we know that the remainder is the same as me plugging that value in. So f of 3 will be 19. That's my last answer. And I highly encourage you, okay? I'm trying to keep the video short, but don't take my word for it. Plug 3 into this guy and see if you don't get 19. Okay, you should. You really should. This process, okay, let me just write a word over here. This is called synthetic substitution. Now, in my notes, I have official definitions for this, okay? Synthetic substitution is when you evaluate a function by using synthetic division, okay? So just kind of like a quick plug for vocab, okay? And remember, this entire process is called the remainder theorem for that guy, okay? What do you think? So far, so good? Now, let's tack on one final thing, okay, that we're going to talk about here. And let me just get my notes real quick. So I have the examples here, okay. We don't need this no more. Let me just bring this whiteboard over. There we go. All right. So let's talk about the factor theorem. Okay, so these next examples deal with the factor theorem. Okay, and the factor theorem is very straightforward. I'm so sorry about the camera. I keep chopping it off here. Okay, the factor theorem states that if, let me write this down. So if f of a is 0 for a polynomial, I'll abbreviate, then x minus a is a factor of the function f of x. Okay? We talked about this in the past already. If my remainder is 0, then that number is a factor. Now, let's do something easier. Okay, what about this? 3 into 12. All right, let's start basic. 3 can go into 12 4 times. Okay, and when I simplify it out, I get a remainder of 0. There's my remainder. Now, because of that, we know that 4 is a factor. It goes in. 3 can go into 12 evenly 4 times. So this is a factor then. Okay. Now, going back to this example that I used to help explain the remainder theorem, you see how this had a remainder? So 4 is not a factor of 14 then, right? Does that make sense? So when we're doing some division problems, that's what we're pretty much doing. If the 0 is a remainder, then hey, that is a factor of it. And we discussed that in some of the previous lessons as well. So now we're just kind of putting a name to it. It's called the remainder theorem. All right. So let's go ahead and try an example out. Okay. So this will be what? Example 3. Just had enough space. I was getting closer and closer to the whiteboard, the end of the whiteboard. Determine if x minus 5 is a factor of this guy. Okay? You could use long division. The reason why I did synthetic is because, like I said, it's a little bit of an easier process a little bit quicker to get to the solution to this guy, but you could use long division. Okay, let's go ahead and set up the synthetic division problem. Okay, always take the opposite of this guy, so it's 5. Put the coefficients down: 1, -7, 7, and then 15. Okay, we'll put some plus signs here, and we carry down the very first value. Okay. All right. So let's go ahead and multiply this out. 1 and 5 is 5. We add, we get -2. Multiply these, I get -10. Add, I get -3. Multiply these guys, I get -15. Add, I get 0. So that's my remainder. So since the remainder is 0, then x minus 5 is a factor of this guy. Okay, so let's write what the answer is. So if I were to factor this, okay, let me write this over here. So x cubed minus 7, oh, I cannot write today, I'm sorry guys. 7x squared plus 7x plus 15, there we go, is made up of x minus 5 times, we'll always go 1 degree less, so it'd be x squared minus 2x minus 3. Okay? So if I multiply these two, I get the original. So then, yes, it's a factor. Okay? What do you think? So far, so good? Now, we're not done yet. You're probably thinking, why? Why are we not done? We could factor this guy a little further, right? So we're really breaking this down even further. Okay, so we have x minus 5 is still one of the factors. Okay. Now over here, what are factors of -3 that when I add them, I get -2? I think that's what? -3 and +1, right? So this could be broken up to x minus 3, x plus 1. So here's this guy fully factored, okay? And we use a little bit of division just to confirm if this is truly what this guy is, okay? So that's what we did. Pretty cool, huh? Really cool, actually. Okay. All right. Now, let's do one more example just to kind of solidify this, and then we'll call it a day. Okay? I think that's a good idea. One final thing. I have another vocab term. When we divided by x minus 5, this is what remained, right? Okay? This part that remains is called a depressed polynomial. Okay? A depressed polynomial is one that has a degree that's 1 less than the original. And it is, right? This is an x squared, which is 1 less than an x cubed. So what remains, the correct terminology for it, we call it a depressed polynomial for that guy. Okay? And once again, full out definition is in my notes, but just to kind of put it with an example, I think it works nicely. All right. One more to go. And I'm going to go ahead, well, let me, there we go. We'll use this whiteboard over here. Okay. So this will be example 4. So we're going to determine, okay, is x minus 2, sorry, let me just bring it up, is x minus 2 a factor of that polynomial? Okay, so let's see if it works, okay? So let's go ahead and use some division. So we'll put a 2 on the outside. Remember, it's always the opposite of this. And then the factors would be, or the coefficients, sorry, 1, -7, 4, and then 12. let's proceed forward. We multiply, I get 2. 2 times 1. Add, I get negative 5. Multiply again, negative 10. We add, I get negative 6. Multiply, negative 12. Add, I get 0. All right. Now, the remainder is 0, which means that, yes, this is a factor of this guy because it works out. So here's what I got left. So it's x minus 2, and then this, my depressed polynomial, is 1 less than that guy. So x squared minus 5x minus 6. Okay? I could factor this a little further, and if you can, do that. So the factors of negative 6 that give me negative 5, well, I believe that would be what? Negative 6 and 1? Okay. So here are all my factors for this polynomial. Okay. So if you divide by one of the factors, you end up getting all the factors for it, which is really cool, huh? Just like we did in the previous example. Okay. One final note, I want to bring this up. If I set this equal to 0, I can solve for the roots, right? Set each one equal to 0, 0 product property. So my x values would be 2, 6, and negative 1 if I do that, which means that the answers to this guy, the x-intercepts, are at 2, 6, and negative 1. So you see how division can help us factor, okay, hence factor theorem, and it can also help us find the solutions to this guy. That's another tool in our tool belt to actually solve polynomial equations of a degree bigger than 2, all right? Like this guy, degree of 3, okay? And that's it. Pretty cool stuff, huh? So we started off with, I can evaluate a function using division, okay? We did a quick proof on that, and then we talked about if the remainder is 0, then it must be a factor, and there's some usefulness with it because we could factor that depressed polynomial afterwards, and this is what it's going to look like. All right? Given that we have some inclination of maybe this could be a factor of it. If the remainder wasn't 0, okay, it's not a factor. We'll just move on. All right? No big deal. But it's not a bad idea to check. Okay? Hope you're doing well. Look at my notes online. They have other examples worked out so you can do some more practice with it. And that's about it. So I'll see you all in the next lesson video. Take care.